So I have 25 minutes, technically 30, but I know there's going to be some questions. So gonna do this fast. So if I talk too fast, somebody could do some gesture or something. I hope this will be a ride for you. So I'm Victor Klang. I work for TypeSafe. Anybody know who I am? Then I don't need to do my bio. Yeah, that's nice. I'm the tech lead of Akka, and I'm going to talk to you about scaling up and out with actors today. But technically, I'm going to talk about Akka 2.0 because we released it earlier this week, so I might as well just upgrade things a bit. So Akka comes from the Sami language, and it's the goddess of wisdom and all the good things in the world. Also happens to be a bad word in Finnish. And that's the view from the summit, so it's pretty awesome. So in case you didn't know, the problem that really led us to build Akka was that it was just way too hard to build correct highly concurrent systems and to make truly scalable systems and to actually make them fault tolerant and self-healing without making everything feel like a duct tape piece of junk. So state-of-the-art tools, right? So the vision is to have concurrency, scalability, and fault tolerance made simpler. It's easy to do it. So how do we do it? Well, we want to manage system overload because there's nothing as bad as you wanting to log on to your internet banking system because the stock market crashed and everybody's just dying to get in there and nobody gets in there. And we want to be able to scale both up on one huge box or scale out on multiple boxes. Or even scale down so you can run Akka on an Android phone or whatever. So scaling in the sense of up and out and elasticity. And we want to replicate and distribute for fault tolerance because you can't really have fault tolerance when you have a single place of breakdown, right? So this also leads it to be a good thing to have transparent load balancing because if you have a big system and you want to be able to manage failure, you want to be able to move things to where there is least traffic at the moment or where there's more RAM available or more CPU available. So who uses Akka? What is it good for and where can you use it? So this is just like a sample of things, like a sample of market segments or use cases, but mainly like finance banking, betting and gaming, telecom and TV, e-commerce simulation, social stuff, which is essentially like a common denominator for where you have lots of transactions happening. And usually varying amounts of transactions. So payday is probably going to be more transactions at the bank or, I don't know, social things probably going to happen some stuff at certain points of time. So Akka 2.0. Why did we make a 2.0? What is it and what did guide us during the process of going from 1.x to 2.0? So to really make a 2.0, you have to have some vision on how you want to improve things. So one of our visions was to design for distribution. So if you design for distribution, then in-VM stuff becomes an optimization opportunity. So if you build it or design it for distribution, it's way easier to do distributed computing and then optimize when things are local. We also wanted to take asynchronicity at heart, which means even in the control things, so creating things, destroying things. Because when you make it asynchronous at heart, it doesn't feel like some sort of hybrid thing that works differently in different ways, and it becomes really hard to reason about how it works. So even for control things, you want things to be asynchronous. Locking and performance on the JVM is really bad when you have contention. So CAS is mother and CAS is father. So everything should be handled using like volatile reads and writes or compare and swap instructions. This has led us to have 0 locks in the hot path, which the difference in performance is astonishing. Also, a problem with the 1.x series was that fault tolerance was sort of a thing that you could choose. The problem is that people normally don't choose things they don't have to choose. So you would write something, and then at the end it was like, okay, now we make it robust. No, you can't do that. So we want to have fault tolerance as the default. So we introduced something called enforced parental supervision, which means that all actors have a parent, and the parent is in charge of supervising the kid. Also, one guiding vision is that there's always room for improvement. So simplify things, refactor things, replace things that are bad. There's always room for improvement. Of course, you have to pick and choose your fights, but question everything and try to see what could be done better. So would that be like a simple version bump, like 1.3, like, yeah, we just bumped the number and let's be over with it? No, technically, we closed 700 tickets. We have changed over 1,000 files. We've added approximately 100K lines of Scala code, removed 57,000 lines. So, to get to like the scaling up and out part of this presentation, not making this like a list of new things added, how do you scale things up? Well, Akka has actors, but it's only one tool in the toolbox. So we have futures, we have data flow, we have typed actors, we have agents, but Akka actors is a good way of scaling up. So it's one tool in the toolbox, but it's not necessarily the tool in the toolbox. There are no golden hammers, not here anyway. So in case you don't know what an actor is, I'm going to try to bring you up to speed within the time limit. So how many of you know about actors? Awesome. So this will be like just refreshing you guys. So an actor is just an entity, an encapsulation of some behavior and potentially some state. And it has a mailbox full with messages, and the circles here are messages. So a thread gets allocated to the actor to take one message, apply the behavior of the actor to that message, and then potentially updating some state, creating some new actors, or sending messages to other actors, or a combination of all of those. New messages can be added while this is happening concurrently, since there is elasticity between the processing of messages and the addition of new messages. And then when the processing of the message is done, the thread gets deallocated from the actor, and it can go on to process some other actor, or even go back to this actor to process the next message. So in Akka 2.0, we decided to remove all global state. There is no global state. We want to be able to have multiple actor systems within one JVM without having to do all this nasty class loader magic. So we introduced something called an actor system, which is the context of your actor application. So this is how we create it in Scala. You'll notice that it will say Scala API everywhere because I've filtered out the Java stuff because you're about as interested in that as no guy. No, the thing is that the Java API is really good. It sort of looks similar as this, but we don't have time today. So what you do is that you specify a name for your actor system. So what is the name of this actor system? And then you can feed it an optional configuration. And this uses the Hocon library, the typesafe config library. Really nice, embedded into Akka for your use. All our defaults are in config files. There are no defaults inside code, which means that if you want to, you can override anything. And we've tried to be really slick with choosing what goes into configuration and what goes into code. Because it's really important that it doesn't become like a new thing where you program in your configuration, but you really want to have things that you would like to change when you're deploying your application, depending on what kind of hardware you're deploying on, or how you have spread your logic out on a certain cluster of machines or whatever. So things that you would like to change when you have built the application should be changed in the config and not in the code. Make sense? So for you that have used Akka before, this is very, very similar, like line by line similar to Akka 1.x. And this is how you create an actor. So you just extend the Akka actor thing and implement the receive method, which is essentially just a partial function from any to unit. In this case, we make an actor that just receives tick messages, updates some counter, and print out the current value of the counter. Then to instantiate this actor, we have something called actor of. And in 1x, it was like a static factory, a global factory. Now it's a property of the system. So this creates one instance of the counter actor in that system and gives you a handleback, an actor reference. And you can see the props thing there. So an actor that doesn't have any props is probably doing some sort of adult movies or something. So an actor in Akka usually have props. So this is like how you configure how this actor should be created. So this is like the type of the actor, what dispatcher it should use. There's more configuration that we'll show later. But this creates a top-level actor, and this is important because I'm going to show you how the structure looks later. When the actor is returned to you, it's already started, or it's going to be started asynchronously. So you send it messages, and it will process those messages after it has started. You can also stop your actor, and you just do system stop and the reference of the actor, and then the actor will be stopped asynchronously. So you won't do any blocking there either. But it will also stop all his children, so you can essentially eliminate a subtree in your application. So, sending messages still looks quite a bit the same. So bang. This is blatantly stolen from Erlang. It's the asynchronous send operation. So it's just fire and forget, move on. It's like the tail pattern. So we have given you an alphabetic name for it as well, for those of you who do not like symbols. And it's a bit easier to use also when you want to explicitly say who is the sender of the message. And the Java API essentially looks the same. We have removed bang, bang, and bang, 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 because at the end it sort of got silly, right? So we only have tell, and this is ask, but it also has the name of the question mark. So it's essentially a request-reply pattern. So you send an actor a message, and then get a future back with the response to this message. It should be used with caution, because if you use this everywhere, you sort of get an RPC-style application. But you can also use ask like this if you want to do that. It's sort of pimped on because we've added it to the Akka patterns. This kind of reads better at times when you want to specify different timeouts for these things. All right, so in 1.x, reply was like, there was probably like 3 or 4 different ways to do replies, getting channels out, getting sender future options and sender options, and now you have sender. That's it. You have sender, and you can send it messages. It's an actorref. So even if you used ask, you have an actorref representing that endpoint that will get the response back. We also still have the become operation to have the actor change behavior, and we have the Java API for that, which looks a bit more interesting. Unbecome to swap back to previous behaviors, because it's a behavior stack, so you can choose when you replace your behavior, you can stack the new behavior, or you can just replace the behavior. So you can also unbecome in the stack. A new thing in 2.0 is something called routers, and they essentially replace actor pools and load balancers. So we have round-robin routers, so it will, when you send a message to a router, it will just round-robin over the children, bypassing the mailbox of the router to have it a high-performance thing, so it doesn't go through one serialization endpoint. We have the random router, which just sends to one random child. smallest mailbox if you want to make sure that the guy with least work queued up gets the message. There's broadcast if you want to send to all children. There's scatter gather first completed, which is essentially saying send to all your kids, and the first guy who responds, give me the result there. So it's good if you have set up some sort of cluster and you want to have a result of a query, and whoever responds first wins. You can also implement your own custom routers if you have like some special needs. And the way you use it is that you have your props, as we talked about earlier. You say with router, you specify your router, and then you specify the configuration for that router. And that's all. And then you get an actor ref back that represents this thing, abstracts over some actors, 5 of them, and it will round robin over them. You can also combine them with resizers, and we have one default implemented. So you have the actor pool, the elasticity of the children. So you can grow and shrink on demand. And the way you do that is that you just specify a resizer to your round robin router or whatever router you use. Simple? So, scaling up. How does this scale up? Well, we did some performance benchmarks because we were using Threadpool Executor under the hood to execute things. And sort of a pattern emerges after some messages there. Can you see the pattern? That's not the scale-up pattern. So we scratched our heads and we elicited some advice from some people, and we had a look and we saw that's an incredible amount of context switches. That's extreme. That's essentially just thrashing your machine. So we elicited the help of Doug Lee, you might know him, to improve the fork join pool for Java 8 to be more scalable. So this is the results we had on our 48-core box compared to the Threadpool executor. Quite a big difference, and
Is it Java 7 or Java 8?
it will probably be in Java 8, but it's available from the JSR 166Y package. But we've embedded that into Akka, so it's the default executor. So around 20 million messages on that 48-core box. It will definitely be different how you use it, what type of messages, and what the processing overhead is, and whatever. But it's still way better than the Threadpool executor. And it looks way better in the context switch department.
Just a question. Was this just no op messages passed today, no processing basically done, so it's only the overhead of actual message passing?
So yeah, so the question is whether this measurement is only for the message passing and not for actual work. So yes, it's only for message passing, because otherwise we would just measure some adder in the CPU or whatever.
It's a very, very bad use case.
Yeah, it's a very bad use case. It just measures what Akka can do. We've optimized things a bit. So an actor is around 400 bytes. So essentially 2.7 million actors per gigabyte of heap. Of course, you will have to add extra memory for messages on top of that, but it says how many actors you can use. Now we come to the fault tolerance part of the presentation, and we have approached this from a let it crash perspective, and that comes from Erlang, and essentially means that you shouldn't try to prevent things from going wrong. You should only have good, decent procedures to handle failures. So in a normal application, OO applications, you will like, okay, if I look at these applications, which parts have critical important state and explicit error handling? And it usually looks really, really bad because it's just scattered across all these objects in this graph. And there is no real order or responsibility here. So there's something called the error kernel pattern. It's essentially like an onion. So you have the core part that you need to protect, and then you have layers on top of that. So if things go wrong at the very core, then your application is hosted anyway. So you add layers of protection around the core. And what that means with actors is you have actors being parents of other actors and supervisors for other actors, and they spawn children underneath to delegate the risk to somebody who is expendable. So if your kid sort of messes up, it will signal its parent, and the parent will decide what happens to the kid. Right? You can also have so that when a kid fails, it notifies the parent, and the parent can decide to say that all my kids, they have some implicit thing that they have in common, so they have to all be restarted if something goes wrong. They're coupled in some way. And you can also escalate problems, so the middle manager doesn't know what to do, so he fails and he escalates to his manager, and his manager decides to just recreate whatever was underneath. So unless failures escalate to the actual kernel of the system, you can always deal with them. So how do we do this in Akka? So we have the parental automatic supervision. In your actor, you have access to something called context. And your context can also create actors, which essentially means create a child for me. So system actor of is create a top-level actor in the error kernel, and this is create a child for me. And you see the name afterwards? This is the name of my kid. I have to name my kid. Otherwise, Akka will name it for you, and it won't be pretty. And also, we've removed UUIDs from any output because UUIDs are horrible in output. So only names and paths. So this parental automatic supervision means that you have a top-level actor, that's the guardian, the system guardian for this system. And when you create a top-level actor, that will be created underneath the guardian. So you create a foo, and he goes underneath the guardian, and he creates a child named A underneath him. And he creates other childs and other children. And do you see what this looks like? Looks like a tree, right? So when you have a tree, you have this really interesting thing in computer science called paths, where you can like get to things through paths. And we thought that was a really smart thing. So when you look up actors, you do it by path. So you can really reuse what you're used to when you work with computers. From the system level, you can just look an actor up, or within an actor itself, you can do relative lookups. Who is my parent? I want to go to this. Who is my sibling? And you can also get to the actual path of the actor. This also means that we can do some really interesting things like doing selections on top of the tree. So I want to have something that represents all things under services. And when I send this message, it will go to all of them. So for the supervision, like how does the parent decide what to do with the kid? So there are two different things, that one-for-one strategy and all-for-one, which essentially means, do all the kids suffer when one has done something wrong, or is it just the kid itself? And this is the how you define like how it will handle failures. So in this case, whenever a child has the actor kill exception, you will stop it. If there is an arithmetic exception, I will just resume the actor, because if he divided by 0, bad guy, but he can probably do something else. You can also decide to restart him, which will essentially recreate him and repopulate him. So something could have gone wrong within him. We need to create a new one of him and restart him. Or you can escalate to say, okay, I don't know how to handle this. Let my parent decide. Yes?
Does his message queue get flushed?
No. All the messages in the mailbox are retained in restart.
So if you're on multiple JVMs, the supervisors deep copied across them? Or
We can talk about that afterwards. Yeah, I don't have it in the slides. And to switch between them, it's fairly simple. You just replace the wording. You can also specify like how many number of times it will actually try to do something about it, and also like the time window that things can occur within. So within the first failure, like within 5 minutes after the first failure, I will accept you to restart 10 times. If things go wrong more than that, something is terribly wrong and I want you to escalate this. And within restart, you have two hooks that you had back in the 1X series. Pre-restart is called on the old actor, and post-restart is called on the new one.
Which thread are these methods called on?
So the question is which thread these messages are called on. These are called on the actual dispatcher. So whatever dispatcher the guy is using. So it will depend on how you configure your app. We have something new in Akka 2.0 which is called Death Watch. And since supervision is only once, you can only have one parent and the parent supervises. But you want to be able to observe when somebody else dies. So if Buddy dies, I want to know. And you will get a terminate message with the ref that died. So then you can match here and say, if it was exactly Buddy, then I will do this. You could also unwatch to say that I'm no longer interested in Buddy because he's a douche or something. So scaling out in 5 minutes. We have new remote actors, so sending messages to actors that reside on other machines. This looks the same as before, like we just create an actor with a name. Your code is agnostic to whatever, like how it is deployed. So the actor name is virtual and is decoupled from how it is deployed. If you don't have any configuration for a path or for a name, then it is assumed to be local. So you can have the same system, the same code, deployed differently depending on how you want to deploy it. So you write your application as if it were local, and then you can deploy it, like distribute it. This also will allow us, in the future releases, to dynamically and change the topology of your system to scale up and out on demand. And this looks like this in the configuration. This path has this configuration. I want it to be a round-robin router. It will have 3 instances, and I want them to be created on these nodes in my topology. This also means that you can have remote supervision. So one subtree is on one machine, and another subtree is on another machine. And some more news in the 2.0 stuff is that we have an event bus API for making it dead simple to do pub sub. There is something called an event stream within your system that is the fire hose of your applications. You can publish messages to the event stream, and other actors can listen to the event stream if you want to decouple your actors from each other so that they do not need to know about each other. We have extensions. You can extend Akka itself. Typed actors, for example, is an Akka extension. The serialization used for remoting is an extension. Essentially, there is no limit in how you can customize your Akka application or add functionality. We have replaced the use of SDM to the Scala SDM, so it's like an API standard, so you can use whatever implementation that implements Scala SDM. And we have re-implemented typed actors to use JDK proxies instead of weaving. So they are now in the Akka actor jar. There is no external dependencies, and they just work. So what's happening after 2.0? So what we want to release as soon as possible is our Camel module, and our AMQP module, and our Spring module. We're going to wait until they are ready, but they will hopefully be ready within a month or 2. So that is what's happening in 2.0 whatever. They will probably be back released to 2.0. So it was as if they were there the entire time, because they don't need any changes in Akka itself. They are extensions as well. This is where we're at. We have a brand new website at Akka.io. Check it out. Check out typesafe.com. And that's it for me. Thank you.
So you have 6 minutes for questions. Just
Yeah,
remember to repeat the
awesome,
question.
awesome. Yeah, so the question is, in a multi-machine environment, how will Akka help me if I lose a machine? So in Akka 2.0, we don't do any sort of trying to find out which node failed how, because it's really hard. But in 2.1, we're going to have a brand new cluster, which is based on the Dynamo paper, on some thoughts behind REAC. But we have adopted it because clustering is normally just trying to cluster data, and we're trying to cluster live objects here. So there's going to be some differences. But then we have a much easier way to have consensus on failure. Because is it just not responding to you? Is it responding to everybody but one? Or is there some other problem? So that we will address in the 2.1 release when we have a bigger picture of what's failing. Because if you only use remoting, you have machines connected to each other, and then, that's a nice applause for that, and then it's hard to know, like, he is communicating with him, but not me anymore. what happens if he sends a message to him and then a message to me? There is no consensus on who is alive or dead. Yeah. So the question is if TypeSafe is going to have like a platform as a service collaboration with some of the, I don't know. Time will tell. It will be really cool to see like ad hoc scaling of Akka applications, absolutely. Okay, so the question is, when you're starting with Akka, how do you choose between typed actors and untyped actors? So typed actors, see them like a doorway between normal request-response code and asynchronous code. So they're more intended to be like the interface between different kind of paradigms of programming. I would try to avoid typed actors because it easily becomes, you try to have the same thinking, but you're doing something completely different. So they don't really harmonize. So pick and choose where it makes sense to have a static interface and always try to either have like a void return type or return a future, because that means you're not doing any blocking, you're just forwarding stuff. So try to see if it makes sense to use typed actors or just go for untyped actors immediately. So the question is, what happened to the OSGI support? The thing is that OSGI is something that you have to like continually test and run, and there hasn't been really that interested. There hasn't been any parties that wanted to use OSGI during the test phase that really, it didn't really make sense then. Also, the Akka actor jar itself is really tiny. So if you want to just deploy the Akka actor jar, I'm sure it's just like 2 or 3 lines of configuration to just use that bundle. Could be harder because we're using SunMISC unsafe, for example. You will have to do some stuff is really hard to do in an OSGI world. So hopefully it will be there, I don't know. If there's enough interest, there will probably be there. Yes? So the question is if we have benchmarked on different JVMs. Technically, yes, but formally, no. We run on different machines with different versions of JDKs, and for example, the 48-core box is running on Linux. So we do benchmark testing, but we don't really have like a formal setup where we have like the exact same hardware, different operating systems, because it's way much overhead. But it's always, I would love to see numbers. So if you guys put up numbers, I'd love to see them. Yeah? Oh, so the question is if there is like built-in support for versioning in Akka, so you can have different versions of messages or actors.
Or when you deploy a new version, can they roll out the node at a time?
So the thing is that for the TypeSafe subscription, you have the Atmos monitoring for your Akka application, and we also want to support provisioning, so you can roll out new releases. Technically, you don't want to do that with a live system. You always want to create some new nodes and take some nodes down, because it's always sort of hard to do a compare and swap on live code. But that's definitely something we're working on. Okay, so the question is if Akka is mostly geared towards stateful architectures and how it handles stateless architectures. So there's nothing really that says that an actor needs to have internal state. But since you have messages, you have state already. And since you're sending and receiving messages, you're actually side effecting and you're actually sending state somewhere or receiving state from somewhere. So you can do completely stateless actors and just have your state in your messages and have your messages be on some storage somewhere. So there's really no need to have stateful actors if you don't want to or whatever the requirements are. So yeah, thank you.